going to talk about an illustration of the importance of this updraft in vertical wind shear effect with regard to a case of a significantly tornadic supercell that affected an area south of Jackson, Mississippi, and central Mississippi in the middle of the night. As you can see in this particular diagram, representative mesoanalysis of mixed layer CAPE showing very marginal amounts of buoyancy present for mixed layer parcel, very limited amounts there, and so the effect, the offsetting effect of the effective storm relative felicity was substantial, as you can see in the bottom chart here, in supporting the significantly tornadic supercell storm south of the Jackson, Mississippi area in the middle of the night. Again, we have very limited amount of buoyancy, but sufficient buoyancy for an updraft to get going in the high SRH environment, as you can see here in central Mississippi. And this is a situation where that interaction of that updraft and the vertically sheared environment supported the development of perturbation pressure deficits aloft and accompanying dynamic lifting associated with the interaction of the updraft and the favorable vertical shear to really support a lot more dynamic lifting than what just the analysis of CAPE alone, the thermodynamic component, would offer. The Hodograph provides numerous clues as to the character of the vertical shear and how it can be instrumental in governing the intricate vital components of convective behavior, including nonlinear updraft enhancements. We're going to make some assumptions before we get started on the discussion of the interaction between the updraft and the vertical shear and how we can use the Hodograph to understand how the ensuing convective behavior would evolve. One assumption is that we're going to meet the necessary conditions for convective updrafts to form, so we just need to have buoyancy. I mean, moisture, some source of lift, instability, combining the moisture and instability to get buoyancy. But again, we're just talking about sufficiency. We're not talking about needing 2,000 joules per kilogram of mixed layer K. We're just talking about sufficient conditions for an updraft. We're not going to consider any components of warm sector geometry that is relative to the flow within the atmosphere in terms of its tendency to support upscale growth through convective interactions. We're going to assume that all convective behavior, mode evolution, is the result of internal dynamics, that is the perturbation pressures that result from updrafts interacting with the vertical shear. And we're not going to be talking about the interactions that take place as separate convective elements interact with one another, like cold pools merging with one another to support convective upscale growth, etc., along a boundary. We're going to just assume that we're dealing with sufficient conditions for updrafts to develop in the vertical shear environment. The ensuing perturbation pressure structure and patterns are going to be driving the internal dynamics to influence subsequent convective behavior. So let's talk about the concept of the perturbation pressure. We're going to think of the perturbation pressure as being a forcing mechanism for vertical motion. Now, this perturbation pressure, again, we're talking about perturbation pressure, we're talking about deviations from a base state, and some of that deviation from a base state could come from what we're talking about as a thermodynamic component, where when a parcel of air is associated with less density compared to its environment, well, a parcel doesn't really know it's buoyant. What we're really having is a deviation from hydrostatic balance in an environment that's thermodynamically supportive of that perturbation structure to support upward motion. Will have the presence of CAPE. Convective available potential energy will translate to convective updrafts, and those are going to be arising from or rather represent a deviation from the base state, in which case the density of that parcel of air is less than that of its surrounding environment. Now, there are other ways, though, for this perturbation pressure to arise in the atmosphere aside from just a thermodynamic component. That would be the perturbation pressure associated with the dynamical lifting that's going to be driven by the interaction of the updraft with the vertical shear profile. I'll refer to that perturbation component as the kinematic component. We can consider that kinematic component as being broken down into a linear component as well as a nonlinear component. Then further breaking down that nonlinear component into a nonlinear component driven just by shear effects, vertical shear of the horizontal wind, and fluid extension effects as well. Now again, the net result here is the development of perturbation pressure, or that is deviations of pressure or mass from a base state that can drive subsequent vertical motion within the atmosphere, both ascent as well as subsidence. And again, these perturbation pressures can come about thermodynamically when we're talking about deviation from hydrostatic balance, that is, one in which we're going to have a parcel of air being less dense than its surroundings, with the presence of buoyancy or convective available potential energy. And then also perturbation pressure that is not a thermodynamically driven component, but rather a kinematically driven component, supporting the dynamic lifting from the vertical shear and the updraft interaction therein. Now, when we talk about the different branches of the kinematic perturbation pressure, we have a component of that, again, that's linear, and that's going to explain not only the down shear propagation of convection from the interaction of the updraft and the vertical shear, but also the deviant cell motion. The nonlinear part explains about how we get these, potentially infinite, although there are many reasons why it's not infinite, but infinite intensification of a rotating updraft, both from shearing effects as well as fluid extension. This does explain, again, those upward motion feedback processes that can result in there being much stronger updraft than what CAPE, the thermodynamic component alone, can provide. However, that does not explain, that is, the nonlinear component does not explain whether a right mover or a left mover or both will be dominant. That's from the linear component. That will explain the down shear propagation as well as the deviant cell motion. All right, in order to continue with understanding these updraft and shear effects, it's going to be important that we appeal to vector analysis. Why? Because vector analysis really is going to be the fundamental governing factor for analyzing the hodograph. The hodograph, not only does it combine all the different horizontal wind vectors with increasing height above ground, but it also is giving an idea of the shear profile, horizontal vorticity profile, and all of these are vectors, effectively a lattice of vectors throughout the vertical wind profile that are going to be instrumental in understanding the vertical shear interaction with that updraft to generate the perturbation pressure structure that influence convective evolution. So let's think about two vectors within the atmosphere. Vector at the bottom of a column in the atmosphere could be an arbitrary column, 0 to 6 kilometers, could be from the base of the cloud layer to the top of the cloud layer, could be talking about the lower half of the storm depth, many different variations of a vertical displacement. We're going to consider a bottom flow, the flow at the bottom of that column, and the top flow. So in this case, the bottom flows from the southwest to the top flows from the west-northwest. And let's say we want to compute the bulk shear within that column, that is the top vector minus the bottom vector. It's what we're going to want to calculate here. So let's again show the bottom vector going towards the northeast and the top vector going towards the east-southeast. We're going to line up the tails of those two vectors at a common point over here. And this is what we're going to use to compute the difference vector, top minus bottom. That's going to be the vertical shear vector. Well, in order to do this, we're going to have to take the bottom vector. If we want to take top minus bottom, it's the same thing as top plus a minus bottom. And so we'll take our top vector, extending from the tail to the tip, and then we're going to take that minus bottom. Again, remember, bottom is going from southwest to northeast, so minus bottom is going to go from northeast to southwest. We're just taking the anti-parallel of the bottom vector. And we're going to take, for the vector, what's really addition over here, top plus a negative bottom. We're going to take that negative bottom, and we're going to, for that vector addition here, top plus and minus bottom, take it from the tip of the top vector and align the tail of the minus bottom vector with that tip of the top vector. So we have top plus a minus bottom. Vector analysis says that that addition of vectors is going to involve taking that vector minus bottom aligning the tail of that vector with the tip of the top vector. And then we'll go from the tail of the top vector to the tip of the minus bottom vector, and that's just the sum of the two vectors right over there. Again, top plus a minus bottom is going to go from the tail of where we're starting the vector addition to the tip of where we're adding the vector onto the top vector. In short, it's going to go from here to here, from north to south, just like that. And we could take that same vector and put that right over here where we've lined up the tails of both the bottom and top vector at the common intersection point over here, or mutual point over here, and it'll go from the bottom vector to the top vector, or that difference vector, that shear vector, is going to go from the vector, from the tip of the vector that we're subtracting out, to the tip of the vector that we're subtracting it out from. So from the bottom to the top. From the bottom to the top. So top minus bottom extends from the arrowhead, or the tip of the bottom, to the arrowhead of the top. So from what we're subtracting out to what we're subtracting out from. So you might think, okay, so why is this important? Well, let's think about it. For bulk wind shear, we're talking about differences in the velocity of the flow, the horizontal velocity, how that differs with height, increasing height above ground. So to compute bulk shear, we can compute this in any layer we want, fixed layer 0 to 6, but to some degree that's arbitrary. There are physical reasons for it. But we can do this for any layer of vertical wind shear. With that incremental layer of vertical wind shear is just computed as extending from the bottom vector to the top vector. That vertical shear vector always will go from the tip of the bottom vector to the tip of the top vector. Well, remember, a hodograph is just a curve that connects all of the different horizontal wind velocities in the vertical profile at a point extending above ground. And we plot all of these on the polar coordinate system. So what that means is that for every point on the hodograph, which indicates the polar coordinate representation of the horizontal wind with increasing height above ground, every layer of air represented by the layer between individual points in the hodograph, or effectively connecting those points with chords on the hodograph. So this is, for instance, one level in the atmosphere, and this is a level above it with a flow at the different levels. On this hodograph, the chord that connects these is the vertical shear of the horizontal wind based on the vector analysis, which means that bringing each of these chords to infinitesimal length, the vertical shear is everywhere tangent or tangential to the hodograph. So the hodograph merely maps out the vertical shear profile. Every single increment, every single set of 2 points on the hodograph are connected to get the vertical shear of the horizontal wind, such that when we bring these displacements down to an infinitesimal distance, the hodograph merely represents the vertical shear profile in addition to showing us a mapping of the wind profile, how it changes with increasing height above ground. That change corresponds to shear, and we also get the exact velocity data at each point above the ground. So everything we need to know conceptually in terms of signs, SIGN, not the sign function, but each term in the perturbation pressure equation can come right from the hodograph. Again, resultant shear vectors connect the layers, or rather the points within layer binding levels lying, again, the shear being tangent to the hodograph. So again, the bulk shear simply connects levels on the hodograph. And as these levels, or the layers in vertical distance, become infinitesimal, effectively that span from the bottom to the top becomes merely a hodograph tangent. And the hodograph sketches out and is parallel to the vertical shear profile. But this is powerful, because if the hodograph is just just effectively a shear profile, everywhere tangent to the hodograph is the shear, then using the right-hand rule, where we stick our index finger in the direction of k hat, which is just going to be perpendicular to the map of the hodograph, effectively in the up direction of the z direction, and we take the cross product between that and the hodograph, or effectively the shear, vertical shear of the horizontal wind, we get the horizontal vorticity, which is always going to lie perpendicular to the vertical shear of the horizontal wind, which will always be to the left of the hodograph going up the hodograph. So not only is the hodograph plotting each level of wind velocity, but we're getting the shear profile, we're getting the vorticity profile. Again, when we stick our index finger in the in the k hat direction, and we put our middle finger down the hodograph for the shear vector, then our thumb, using the right-hand rule, will stick to the left of the hodograph. You can try that out on your own if you'd like, representing the horizontal vorticity vector, which will again always be perpendicular and to the left of the hodograph sketch. This is very powerful. The hodograph demonstrates so many different concepts simultaneously.